So let us learn about Galilean transformation. We begin by considering the concept of a physical event. The event might be the striking of a tree by a lightning bolt or the collision of two particles, and it happens at a point in space and at an instant in time. So, physical event is anything that occurs at a point in space and at an instant in time. An event can be specified by an observer by assigning to it four coordinates. So what are these coordinates? So first is the three position coordinates and the time coordinate. So for the position coordinates, we have x, y, and z. And for the time coordinate, we have t. So consider now two observers, O and O prime, where O prime travels with a constant velocity v with respect to O along their common x and x prime axis, as seen on the figure. Both observers are equipped with meter sticks and clocks so that they can measure coordinates of events. Further, suppose that both observers adjust their clocks so that when they pass each other at x equals x prime, which is equal to 0, the clocks will read t equals t prime equals 0. Any given event, p, will have 8 numbers associated with it. So the first is the coordinates assigned by O, which is x, y, z, t, and the coordinates assigned by O prime, which is x prime, y prime, z prime, and t prime. Now the relationships between these coordinates assigned by O and O prime for a particular event is obtained by examining the previous figure, so this figure. So from here, we can see that the observer O prime is moving at constant speed v with respect to the coordinates of observer O. So the prime coordinates are related to the unprimed coordinates by this equation. So we have x prime equals x minus vt, y prime is just equal to y, z prime is equal to z, and t prime is equal to t. These four equations are called the Galilean coordinate transformations. In addition to the coordinates of an event, the velocity of a particle is of interest. Observers O and O prime will describe the particle's velocity by assigning three components to it, with u sub x, u sub y, and u sub z being the velocity components as measured by O, and u sub x prime, u sub y prime, and u sub z prime being the velocity component as measured by O prime. Now the relationship between ux, uy, uz and ux prime, uy prime, and uz prime can be obtained from the time derivative of the Galilean coordinate transformations. Thus, from here, x prime equals x minus vt. We can take the derivative with respect to time. We have dt of x prime equals d dt of x minus vt. So we have u of x prime equals u of x minus v. And for the y and z components of the velocity, we will have u sub y prime. U sub y prime is just equal to u sub y, and u sub z prime is just equal to u sub z. So these are the Galilean velocity transformations. And the acceleration of a particle also can be obtained by taking the derivative of the velocity transformations with respect to time. And we use the fact that t is equal to t prime and v are the speed of observer O prime is constant. So we have from our velocity transformation, we have u of x prime is equal to u minus v. So taking the derivative with respect to time, we have u sub x prime equals the derivative of u minus v. So we have u, derivative of u of x prime, we call it a of x prime, which is equal to the derivative of u with respect to time. We can call it a of x. And then the derivative of a constant, this one is a constant, so that is 0. So we will get a of x prime is just equal to a of x, and likewise, we will get a of y prime is just equal to a of y, and a of z prime is just equal to a of z. So take note that the measured acceleration components are the same for all observers moving with uniform relative velocity. Now we define invariance of an equation. So this means that the equation will have the same form when determined by two observers. So based on our previous result that acceleration is invariant under the Galilean or the classical transformation, then it is apparent that Newton's laws of motion, the law of acceleration, F equals mass times acceleration, is also invariant in classical transformation. Now let us take a look at the classical Doppler effect. There is one other classical relation that deserves consideration, which is the transformation of sound frequencies. It is of interest to know how the frequency of sound waves transforms between inertial reference frames. Sound waves are recognized as longitudinal waves, and unlike transverse light waves, they require a material medium for their propagation. Assuming a uniform material medium, the speed of sound, or the speed at which the waves propagate through a stationary material medium, is constant. The basic relation we have v sub s, or the speed of sound in air, is equal to lambda times the frequency. So we have here the wavelength of the wave, and then we have the frequency of the wave. Classical physics requires that the relation expressed in this equation is true for all observers who are at rest with respect to the transmitting material medium, which is air. That is, once sound waves have been produced by a vibrating source, which can either be at rest or moving with respect to the propagating medium, the speed of sound measured by different spatial observers will be identical provided they are all stationary with respect to and in the same uniform material medium. Certainly, the measured values of frequency and wavelength in a system that is stationary with respect to the transmitting medium need not be the same as the measured values of frequency and wavelength in a moving system. Now, to deduce the classical frequency transformation, consider the source of sound waves to be positioned at the origin of coordinates of the S' reference frame. So this is the source, or we can call this the emitter. So this one. Let the sound waves be emitted in the direction of the listener, which is located at the origin of coordinates of the unprimed system and is stationary with respect to air. So this is the picture. The wave pulses of the emitted sounds are depicted by arcs. So this one. The wavelength can be written as x over n, where x is the distance between the source and the listener, and n is the number of wave pulses perceived by the listener. So solving for the frequency, so we have the frequency f is equal to v sub s over lambda. So we have the frequency is equal to v sub s over lambda, where lambda is equal to this equation. So we have f is equal to v sub s divided by, we have here lambda, which is equal to x over n, or we can just write this as v sub s multiplied by the number of wave pulses as perceived by the, the listener over x. Now, as we can see from the figure, we can define x. We can write x as this is equal to uh, x is just equal to v sub s multiplied by delta t plus u times delta t. Or we can just write this as v sub s plus u multiplied by delta t. So this equation for f here can be rewritten as f is equal to v sub s multiplied by n divided by our value for x. So we have v sub s plus u multiplied by delta t. Now, by inspection, we can see that the number of wave pulses can be obtained by multiplying, we have the number of wave pulses is just equal to n prime, which is also equal to f prime times delta t prime. Okay, so there are two frequencies now. This frequency f we denote as f. This is the frequency as perceived by the listener, or the frequency as heard by the listener. And then f prime here, this is the frequency emitted by the source. So this is the proper frequency. Okay, so that our f can be written as v sub s multiplied by f prime delta t prime divided by, we have, shall I write it here, divided by v sub s plus u multiplied by delta t. Okay, so let me just copy it here. So we have now this equation, f equals f prime multiplied by v sub s times delta t divided by v sub s plus u multiplied by delta t. So this one is delta t prime. Okay, now it has been established that delta t prime is just equal to delta t. Time is absolute in the classical transformation. So therefore, this one can be cancelled out. So we are left with, we have v sub s times f prime over v sub s plus u. Okay, so this is our frequency. Now if we take v sub s out, so we have v sub s f prime over v sub s. We take v sub s in the denominator out, so we have this is 1, and then this one is u over v sub s. We can cancel this out, so we are left with f is equal to f prime over 1 plus u over v sub s. Now we define kappa being equal to 1 over v sub s. So we can write the frequency equals f prime over 1 plus kappa. Now, you can see here that the denominator 1 plus kappa is always greater than 1. So 1 plus kappa is always greater than 1. Meaning to say, the frequency as heard by the listener is always lesser compared to the frequency emitted by the source. And finally, we can calculate for the wavelength. So the wavelength can be obtained by dividing the speed of sound by the frequency. And as we have obtained earlier, we have the frequency is equal to f prime over 1 plus kappa. Therefore, our lambda, the wavelength, is equal to v sub s over f prime over 1 plus kappa, or this can be written as v sub s multiplied by 1 plus kappa divided by f prime. Note that v sub s, we have to note that v sub s over f prime is just equal to our lambda prime. So we have this expression, lambda is equal to lambda prime 1 plus, we have lambda is equal to lambda prime multiplied by 1 plus kappa. Now take note that 1 plus kappa is always greater than 1. Therefore, so we have lambda is always greater than lambda prime, or the wavelength as perceived by the receiver or the listener is always greater compared to the wavelength of the wave emitted by the source. Now we can also show that for another case, we have a stationary listener and we have a source that is moving towards. We can show that our f, or the frequency as heard by the receiver in this case, is equal to f prime over 1 minus kappa, and the wavelength is equal to lambda prime multiplied by 1 minus k. So let us try to obtain these values or this expression for f and lambda. So as you can see from the figure, we can deduce here that our x is equal to v sub s delta t minus u multiplied by delta t, or we can just write v sub s minus u multiplied by delta t. So recall also that our n is just equal to our n prime is equal to the frequency as emitted by the source multiplied by the time interval delta t prime. So from our expression, we have f is equal to v sub s over, we have lambda, where lambda is equal to x divided by n, or the distance between the emitter and the receiver divided by the number of pulses. Okay, so we have f equals v sub s multiplied by n over x. So we have v sub s multiplied by our expression for n, which is just f prime times delta t prime, divided by our x, which is v sub s minus u times delta t. And using our Galilean transformation for time, delta t is just equal to delta t prime. So we can just write frequency. Frequency is equal to v sub s times f prime over v sub s minus u. Or we can write this as, we have v sub s times f prime, and then we take out v sub s in the denominator, so we are left with 1 minus u over v sub s. Okay. And then we cancel v sub s out. So we have this one, f prime over 1 minus kappa. So this is our expression for f. We have obtained this equation. And for lambda, we just have to substitute our expression for f. So we have v sub s over, we have f prime over 1 minus k. So we have 1 minus kappa over f prime. So take note that this expression here, v sub s over f prime, is equal to lambda prime. Therefore, we can write it as lambda prime multiplied by 1 minus kappa. Okay, so here we can see that for a stationary listener, and we have a source that is moving towards the listener, the frequency as heard by the receiver is always greater compared to the actual frequency, and lambda is always lesser compared to the actual wavelength. So this is for the stationary listener, and the source is moving towards the listener. Okay, so for your assignment, you have to show that for a stationary source and we have a receiver that is moving away from the source, we can obtain these values of f and lambda. And also, we can also derive these equations for the stationary source and the listener that is moving towards the source. Okay, so this will be your assignment.